Hi friends, this is Dr. G. Srinivasa Gupta, Professor from Mechanical Engineering of VIGNANA JYOTHI Institute of Engineering Technology. As part of Dynamics of Machinery course, today we are going to discuss mechanical vibrations. That introduction part of that mechanical vibrations, we will see how vibrations arise and what are various types of vibrations and what are its applications. We are going to see all this and how we can simple form of expression we can develop in vibrations. What are the advantages of vibrations also we are going to see. So, what are vibrations? Mechanical vibrations refers to the oscillatory motion of a body about its equilibrium position. From equilibrium position, when we displace a body from equilibrium position, means we are giving a work against constraint forces. So the body is constraint elastic forces. So the body is going to displace and it gains potential energy. In turn, the internal forces are going to bring the body in equilibrium position. Then this potential energy is going to be converted into kinetic energy. Again this body is, because of this energy, is going to move. Work will be done against elastic constraint forces. Again body is going to come, trying to come in its equilibrium position, that is converted to kinetic energy. This is repeated continuously. So the body oscillates unless there is no resistance or resistive force exerting on the body. So when a system is disturbed from its equilibrium position, that means rest position, it tends to move and back forth due to restoring forces. So it's gaining strain energy because of strain or potential energy, we can say, because of it is giving some work on to displace from equilibrium position. Then it is going to convert that transformation of strain energy into kinetic energy when it come to its equilibrium position. Then again, because of this kinetic energy, body is going to get some work on elastic constraint forces. Again it is going to convert into potential energy. So this transformation of potential to kinetic energy, kinetic to potential energies keep on continuous when body is oscillating, okay, unless there is no resistance against this oscillatory motion. This motion repeats periodically or non-periodically also. We will see the details. First let us see what is the body must be elastic and it has some mass. When elastic body is given some displacement, then these internal, that is the forces are the work done on elastic constraints. Means body must be in elastic property, and it has some mass. Because it has some mass, then only it is going to have some mass and energy it gets. Okay, so to develop a model, we are going to take this as a mass element and spring. Okay, sometimes if some resistance is also going to take place on the body to stop this motion, that is called element damper. So mass and spring is for elastic force, because spring we know that it will restore that force. Once it is pressed, again it's come into normal position to restore its original position. Means absorbing energy and restoring back. Okay, so this is the spring is going to do that part, and mass stores kinetic energy. Okay, spring is elastic element, means stores potential energy, we can say strain energy. Okay, so potential energy to kinetic energy or strain energy to kinetic energy to strain energy conversion takes place while the body is going to oscillate. If it is stop its motions due to some resistance, that is the element which is providing is damper. We are going to see in details. So we will take the a mass attached to the spring moving up and down. Suppose this is the spring. Okay, a mass is attached. Let us say mass m. This spring have some elastic property, that is stiffness. Then, okay, so if you displace this mass, okay, some displacement x you give, then this mass moving down means it is having some gain, spring gain, potential energy or strain energy. Then again it restores, it goes back, okay, move up and down motion, okay, to restore it. This is the example. And vehicle suspension system, you know that, okay, there spring and absorber is there, spring compresses and again it is going to release that energy. Engine components we have seen. So what we need to understand, in order to understand it thoroughly, we need to understand some important terminology involved in this. Terminology means, okay, for example, with this spring mass system, we are going to get some clarity on these terms. Cycle. Cycle means one complete oscillation. Here in case of, it is moving down and up. This is one oscillation. We can say that is cycle. Similarly, amplitude, maximum displacement it has got. Suppose it is displaced some amount, delta. So this is the maximum displacement, and again it move up and come down. So this is maximum, and slowly this, because of restoring force, this is slowly this displacement is going to decrease. And time period, time for one cycle, one complete cycle, okay, one complete oscillation, how much time it is taking, that is time period. Frequency. Frequency means per a unit time, how many number of cycles complete. If you measure for 1 minute, how many complete cycles it is completing. So these cycles per 1 minute if you write, that is cycles per minute you write in terms of seconds, then you can express in cycles per second. Okay, time period is time for one cycle. For one cycle, time. Okay, so each cycle, how much time it is taking. Frequency means number of cycles per second. Number of cycles and time taken, that ratio will give frequency. Suppose n oscillation it is, then n by time taken for n oscillations. Okay, that is n by t is frequency. Each oscillation, how much time it is taking, that is time period. Okay, natural frequency means frequency at which system vibrates freely, means there is no resistive force to stop this motion. It is continuously transformation of kinetic energy to potential, potential to kinetic, or kinetic energy to strain, strain energy to kinetic energy. Okay, this is freely, but means the motion is continuous. There is no stop once you disturb it and leave it without applying any force further. Then it is called natural frequency. Frequency at which system vibrates freely. Okay, number of cycles per unit time, that is natural frequency. Okay, I think you are able to understand little bit. Types of mechanical, coming to the types of mechanical vibrations. Okay, different criteria, based on different criteria we are going to classify these vibrations. Based on excitation, you are giving the disturbing force or displacing force. So pre-vibration, first one is pre-vibration. This excitation is given and leaving, and no more any excitation need to be given. Then it continues oscillation. So this occur when a system vibrates after an initial disturbance. No external force acts after release. Example, pulling a spring and letting it go. Then it is continuously oscillate. Similarly, force vibration, second one. You are going to give a continuous external force. Example, engine induced vibrations in machines. There is continuous force, exciting force. We are going to apply some force to disturb continuously. Okay, if periodically in certain intervals, then that will vibrate. That is called forced vibration. We are giving disturbing force continuously. Okay, then other way of classification is based on energy dissipation. In that, first category is undamped vibrations. So in undamped vibrations, no energy loss because no resistive force some external agency is not contributing to stop the motion, then this is called undamped vibrations. No energy loss, continuously transforming one form to other form, kinetic energy to strain energy, strain to kinetic, continuously. So motion continues indefinitely because no resistance against this motion, external resistance. Second category is damped vibrations. Energy is lost due to friction or resistance, air resistance or some other resistance. Okay, the energy is going to absorb because of that resistance against acting. So amplitude gradually decreases because of resistance. Okay, see this need some damping element, means which is going to absorb energy, that element required. Of course, we are going to see details of damping element and all those, but different types of damping elements or we can provide is light damping, critical damping, heavy damping. Means it will stop very quickly, heavy damping. Critical damping is it will take one oscillation or few oscillations. Light damping means it take more oscillations to stop. That means resistive force of stopping this motion is very low. Are able to understand damped vibrations and undamped vibrations. Third category is based on linearity. These vibrations may be linear, means force, application of force directly proportional to displacement. Depends on application of force, the displacement is there. Suppose force versus displacement if you draw, then it may be some particular sort of relation. So it is sinusoidal relation. It is continuously some linear. Okay. Similarly, non-linear means force not proportional to displacement. Okay. So in this case, suppose force not proportional to displacement, force and displacement, it is a zigzag, random. Okay. So that is non-linear vibrations. It is complex behavior. We cannot say sometimes how it is going to happen. This is complex behavior and force not proportional to displacement. Okay. There is no particular relation we can say directly. Okay. So next category is based on motion. Okay, based on motion we can have three types of vibrations: longitudinal vibration, transverse vibration, torsional vibration. Longitudinal vibration, it is very clear along the axis of along the length. If you apply some disturbance, okay, suppose if you take same system, spring mass system, okay, mass is this one. Along the length, spring length is this one, this direction. If you apply some force, then it is going to oscillate along the length direction. Is it or? Okay, or some shaft which is attached and a disc is attached end of this shaft, let us say. Then if you give along the shaft length, you are going to give some disturbance, then it is going to oscillate in that direction only. Okay, motion along the axis, compression of rods and tension also, you can say if you pull it or push it, this is motion along the axis. Then there may be some vibrational effect, that is longitudinal vibrations. Transverse vibration means it is obvious that you are going to give motion perpendicular to the axis. Of course, you are giving such a way that the motion, it is one time the shaft is moving in this direction and other time it is going to move in this direction. So this means it is transverse vibration. You are applying disturbance perpendicular to the axis initially. You are going to understand this. Third one is torsional vibrations. You are going to just give the twisting motion. Twisting means just rotate this disc. Okay, rotate along the axis, rotate. Rotate means you are going to give rotational motion. This is angular motion, we can say. So shaft twisting in engines, because all the engine shaft carries parts which are rotating motion. So it is going to twist, okay, somehow, some amount. That is, these are the three types of vibrations based on motion. So now coming to the other category based on system characteristics. Deterministic vibrations, okay, predictable forces. As we have seen, it is a linear vibration and non-linear. Similar fashion, deterministic vibration is predicted, forces can be predicted, and non-deterministic here. Forces can be sinusoidal variation, force versus displacement. Suppose we can predict, we can write some relation. Okay, random vibration means unpredictable forces. We cannot write some straightforward equation. Examples also, earthquake and wind loads. Wind load suddenly, because based on the pressure of the wind, suddenly comes and suddenly rises, suddenly down. So this is unpredictable. Okay, these are called random vibrations. So these are all based on system characteristics. Deterministic vibrations, this is predictable. Undeterministic means random variables, unpredictable forces. Okay, these are the types of vibrations. Okay, the important concept here is, suppose it is predictable, simple harmonic motion. So if we say simple harmonic motion, so then this is going to, okay, we are going to give some spring mass system I am taking in the initially beginning to make you understand. If you just displace it, it will oscillate. Okay, so the force which is going to, if you take free body diagram of this mass, okay, it is, we are applying displacement, means it is some acceleration. Acceleration we can write mass into x double dot. Okay, x double dot means d square x by dt square. Displacement, you have x. Velocity you can say x dot dx by dt, and acceleration is d square x by dt square. Why I am going for acceleration is mass into acceleration will give force. Okay, so the force with which, because of acceleration, it is going to have the amount of force we are applying for this displacement, we can say m d square x by dx square. We are applying this force. Then here in this direction, because it is free body diagram of mass, then here spring has some stiffness scale, let us say. Stiffness means load required for unit deflection. We have given x displacement. Then again this elastic material which is having a property of stiffness k, then this force, okay, restoring force we can say kx, acting in upward direction. Then these two, based on equilibrium condition, requires the forces must be balanced. Okay, what are the forces? This is in opposite direction. Mx double dot, this is acceleration force, is equal to minus kx. Okay, you may see that equilibrium equation, right? All the sum of forces equal to 0, means this accelerating force induces inertia force opposite to the accelerating force. This is inertia force. That is, we can say same, magnitude is same in opposite direction. So what D'Alembert's principle tells? D'Alembert's principle tells inertia forces and whatever internal forces, okay, this should be balanced. That is, algebraic sum of all these forces must be 0. That is D'Alembert's principle, as you know in dynamics. Then we can write this same equation we can write mx double dot. This is inertia force, okay, same direction, plus kx equal to 0. K into x. X is displacement, k is stiffness. Small k will write, lower letter. This is the equation. Okay, are you able to understand? I think simple harmonic motion is concerned, that is, okay, motion is sinusoidal. How we are correlating with that we will discuss just soon. Basis for vibration analysis. Okay, this is the basis. This f is f plus f equal to minus kx is the basis for vibrations. Are you able to understand what is this f? Inertia force equal to kx. Kx is restoring force. Okay, so this is this basic equation we need to understand. Now coming to the, we will discuss in detail regarding this expression for vibrations. So writing some expression, how do we write in different cases, and this equilibrium of these all the forces, inertia forces and restoring forces, or you can say this is the reactive force kx, and this is the inertia force acting upward. So we can write this equation. Okay, fi plus kx equal to 0. Then fi means mx double dot, magnitude is same, plus kx equal to 0. Now coming to the applications of mechanical vibrations. As we have experienced in our day-to-day activities or experiments, if you go through it, then we can find so many, we can experience also vibrations. So what are the, in engineering aspects are concerned, engineering applications in machine design, what is the purpose of studying these vibrations? To avoid resonance. Resonance means we will discuss in detail, but the natural frequency, if there is no exciting or additional external force to stop this, then it continuously vibrate. Okay, then you write some frequency, develop some expression for frequency, that is called natural frequency. If you apply some force to stop this motion or oscillations, then that is called force of frequency of the force which we are exciting force frequency. So then you can, if these two are equal, exactly equal, the system will collapse. That is called the phenomenon of resonance. So in machine design, while designing various parts or elements of the machine, we need to check that the natural frequency of the part, which should not be coincide with the forces sectionally acting, the frequency of exciting forces, sectional forces. So we need to design the parts such that these two must be have some much difference. Never the machine operates to become equal these natural frequency and force frequency, external force frequency. If it is equal, then there is a great damage and collapse of the machine, failure. That is called a resonance condition. Engine balancing also. To reduce vibrations, we are going to see balancing of engines, because engine carries rotary parts. Then if there is any unbalance, that leads to vibrations. Okay, unbalance of force. Okay, gear and shaft design, all these we are going to discuss in detail as mechanical engineering is concerned. Similarly, civil engineering, earthquake resistant structures, bridge vibration analysis, these are all we need to understand vibration aspects of these. And automotive engineering, of course, suspension system, ride comfort and stability. Okay, we are going to test the vehicle before going to release the actual vehicle model. It's thoroughly testing is going to be carried, and that must be confirmed with vibration aspects are concerned, then only released in the market. Now coming to aerospace engineering, aircraft wing vibrations, rocket dynamics, there is vast subjects. People are going to thoroughly analyze and giving solutions. Manufacturing industry, vibration conveyors, screening machines, ultrasonic machines, any machine tools, all these are thoroughly analyzed for vibration aspects. And measurement and instruments also. Example, seismographs, vibration sensors, condition monitoring systems, all these are comes under these instruments and measurements. And why we need to study vibrations? In all these applications we have seen, our basic object is to prevent failure due to resonance. Second one is improve machine life. If unnecessary vibrations creates additional stresses in the machine component, though the components which are not properly designed, it loses its durability or life. Okay, and enhance performance and safety also. Sometimes safety aspect is most important. Okay, if high speed machines, the large number of vibrations, huge vibration, high magnitude vibrations leads to high stresses, and sometimes safety is also very much concerned. So other reason is importance is to reduce noise and wear of the parts which are having relative motion. So these are the important significance of studying vibrations. See this some sort of expression is concerned. How do we develop expression for undamped vibrations? Just I have mentioned this vibrational model need to be some mass. Mass is load, and some spring stiffness, that is elastic property of that mass. So any object must have some mass and elastic property. That's why we are taking spring is elastic material and some mass. This is the model we are taking. But in general, any object must have some elastic property as well as some mass. That is the meaning of this one model. So this mass is if it is free undamped vibration, there is no external resistance and it is freely oscillating. If you just initially giving some disturbance, that means displacement, and leave it. Then it is freely oscillates. Okay. It is if it is elongates, then some strain energy is developed, and again it is going to move up, then some kinetic energy. Okay, this continuously oscillate to transfer these energies in between these two. Okay, so the force acting because of this displacement x given, the force acting on this is, we have seen just now, this is the resistance reactive force, spring stiffness into x upward direction kx, and the force which is going to applied in downward direction, you know that if you know mass, then you can say mx double dot. X double dot is as usual d square x by dt square. This is the one. So obviously we could write the relation because this is acceleration force, then inertia force. Inertia force is opposite to the direction of motion, and magnitude is equal to same. So we can say that this force equilibrium, or you can directly write this relation. This whatever the acceleration force must be equal to, okay, this must be equal to this is opposite direction minus kx. Then that's why it is inertia force I am showing upward direction. This is called inertia force equal in magnitude. Okay, so these inertia forces and this external force, this must be balanced. That means mx double dot plus kx is equal to 0. Then it is in equilibrium. So standard form we can write. How we have written x double dot, okay, plus k by m. This same thing we can write into x. Both sides, both terms are divided by m. Then you can have this one. This we can write x and k by m. You can write sometime k by m plus omega n square x equal to 0. Here omega n is natural frequency. Omega n. What is omega n square? K by m. So omega n is root k by m. So this is the concept of natural frequency. How do we find? Means the stiffness coefficient, that is k, stiffness value, and m, a mass, some mass. So each object must have these two, then it has some natural frequency which can be written like this. Okay, so suppose for example, more clarity required, then this is the spring. Okay, once you attach the mass, what happened? See, this mass leads to some, let us say this is going to displace because of attaching the mass. This is the spring initially, it is getting this displacement. How much displacement it is getting? Let us say delta. And this is the force, how much force applied on this? mg. Is it or not? Okay, this is the force applied. Then if you write, okay, it is standing here. Once you attach this just mass, then it is standing here. This is the, if you write, okay, take equilibrium of this mass, then here mg, here is how much? Delta is the displacement. I said it is now in stable position. Then k delta is force opposite to this, spring reaction on this. Then you can see that this is the, you can write mg equal to k delta. Mg must be equal to k delta. Then you can write k by m is g by delta. Here you can use, if you know amount of static deflection, this delta is called static deflection because once you attach the mass to the spring, then it is getting delta amount of displacement from along the direction of axis, then it is stable, okay, because of this mass. Then that is k by m, also you can say g by delta. Delta is static deflection, you can say. Then you can write here g by delta also. So omega natural frequency is square root of g by delta. For a certain amount of mass you attach, then if you find delta deflection, how much it is, okay, coming elongated, then that is g is gravitational constant. Square g by delta will give natural frequency square. So natural frequency you can also evaluate square root of g by delta or square root of k by m. This is square part. And okay, so if you want natural frequency, then you can write k by m or g by delta. Okay, this is units are, you will have radians per second. Okay, so this is about all this. So if you write, okay, how do you get, as it is said, time period? Time period is, how do you get time period? You can write omega by, omega is natural frequency we said, cycles per second. Okay, so time frequency omega is equal to 2 pi f. That is, okay, this is cycles per second. So 2 pi by omega is 2 pi by t. Because why 2 pi I am writing, it is said cycles per second. Each cycle 2 pi, okay, amount of radians it is taking. That is 2 pi. F is the frequency. Frequency, what is the definition we have seen in the term? Frequency is, okay, frequency is number of cycles per second. Frequency simply. So why we have written 2 pi, you are able to understand now. Number of cycles per second is frequency. I am saying radians per second, this omega n. Then 2 pi into each cycle 2 pi. Okay, in terms of angle you can say. So 2 pi f is omega, radians per second. Then, okay, f is cycles per second. For one cycle, how much time it is taken? That is time period we said. Then cycles per second is, okay, this is inversely, this is 1 by t. Time period we want 1 by f. So 2 pi by t is same as 2 pi f. Okay, that is omega n. You can write. Okay, 1 second, how many cycles? Okay, like that. Okay, each cycle how much time it is taken? Cycles per second. Okay, one cycle how much time? That is, you can write time. That is the time period. Okay, 2 pi by t is also omega n. Okay, f is 1 by t. Okay, this is cycles per second. For one cycle how much time taken? That is t. Okay, reverse. Okay, it is all about this. Okay, we will see if damper is there, then that equilibrium, that mass, how it is going to be forces acting if you isolate and draw free body diagram. This is, you know, that spring stiffness and x is the displacement given. Then it is, the spring is elastic in nature, this elastic force kx, and this downward we are giving mx double dot. If there is a damper also, one more element attached, not only spring. This is the spring, okay, mass attached. This is the damper, let us say, damper. Okay, damper, damping coefficient C, we will see the definition. Spring constant is K, spring stiffness. Damping stiffness, we can say C. Then a mass is attached, M. Okay, this damper, the purpose of damper is to resist the motion. Okay, then this damping is coefficient is defined such that Cx, okay, C is, the here spring is force per unit deflection. Here it is force per unit velocity. Okay, Cx dot. We will see detailed how it is going to be defined. Damping coefficient is force per unit velocity. So it is C into x dash t velocity term. So this is force, and kx is the spring force, spring stiffness into displacement. Okay, restoring force and restoring, and this is mx dot. This is acceleration force. Then inertia force, if you want to take, this is opposite to this. Instead of this inertia force, if you consider, or you can write this downward, this acceleration force must be equal to this kx, the opposite direction, kx minus cx dot. Then you can write mx plus kx plus cx dot. Here dot dx by dt, double dot dx square x by dx. This is 0. Okay, so you can simplify this and write some using some damping factor. Damping factor, how it is defined is, if you divide all the terms by, okay, m, then you are going to get c by m x dash equal to 0. This is, you know, that k by m is omega n square x, and c by m, if you use some damping factor 2 zeta, it is zeta. Okay, 2 zeta, okay, 2 zeta wn x. if you write such a way that, then what happened, this zeta is called damping factor. What is this zeta then? It is C by, you know that, you can see. If you write 2 zeta omega n x, then zeta becomes, because it is C by m term only, then zeta becomes 2 times square root of km. Okay, so this is the zeta is called damping factor. This is damping coefficient by 2 square root of km. Further details we are going to study in detail in our coming lectures, and a few examples also, practical examples. What happened, this damping coefficient, different values, that also you can just see. If it is under damped, means very less light damped, then oscillations will continue. Okay, a certain amount of time. Then this zeta is less than 1. If zeta is equal to 1, then it is fastest return, means with few oscillations it is going to stop. And over damped means if zeta is equal to, that means more this value, zeta greater than 1, then this damping coefficient is more, it will stop without any oscillations immediately. So these are called 3 cases: under damped, critical damped, over damped. Further explanation and details about this damping we are going to see in our next lecture. With this, I am concluding this lecture here.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.